Hi everyone, welcome to part 1 on our video lectures for section 3.7 dealing with the chain rule. In this set of videos, we're going to go ahead and review function compositions and then learn about the chain rule. Now, to recap what we covered so far, we've seen how to take derivatives of polynomials and the natural exponential function, as well as functions that are multiplying and dividing, and even the trigonometric functions. Now, the question is, can we take derivatives of composite functions? Well, you bet. And this is where the chain rule will come into play. But before we do that, let's go ahead and review function compositions. If we have two functions f and g, then the composite function, read here as f composite g, or the composition of f and g is defined the following way. The composite of f and g is simply f of g of x. Now, we get to see here that a function composition is nothing more than a function being evaluated at another function, or in other words, it's a function inside another function. Now, before we learn how to take derivatives of function compositions, I want to get some practice recognizing a function composition. So let's take a look at the following example, where for each of the following functions, we see if we can identify two functions f and g such that the h of x that we see can be reinterpreted as the function composition f composite g or f of g of x, which in fact I'll write here. Now, from now on, since the g function is the one inside, I'm going to go ahead and refer to my g function as my quote-unquote here inner function, and f as my outer function. Okay, so with that out of the way, let's go ahead and take a look at our first function, where we're being given h of x is equals to the square root of x squared plus 1. Alright, so how can we go ahead and rewrite this one here as a function composition f of g of x? Well, I always recommend you guys to identify what seems to be the function that's inside some other function. In other words, what is our inner function? Well, in this particular example, I am taking the x squared plus 1 and I'm placing it inside of the square root. So that means here that my inner function is going to be my g of x, which is the x squared plus 1. Alright, so we're placing the g of x inside of what? Well, we're placing it inside the square root function. So my outer function here, f of x, will be the square root of x. Now, does this function composition work? Well, let's see. I'm going to go ahead and check if my function composition was correct by evaluating f of g of x. So again, here a quick refresher for the function compositions. We're basically taking our outer function f and evaluating it at our g function, which was x squared plus 1. So let's see, if we place the x squared plus 1 inside of f, now what was the function f doing? The function f was telling you to take the square root of whatever your input was. Now in this case, our input is x squared plus 1. So I'll put my input x squared plus 1 inside the square root function, and lo and behold, we do indeed get the h of x function here. Perfect. Now, if you're a little bit rusty on function compositions, I do recommend to take a look at the previous recordings on the review for function compositions to help you guys feel more comfortable with the material. Okay, let's take a look at the next function. Alright, so we're being told that h of x is equals to 7x squared plus 5, and then the whole thing is being raised to the third power. Okay, once more, what seems to be the function that we're placing inside? Well, it looks like we have the 7x squared plus 5 inside of the cube function. So in this case then, my inner function, in other words the g of x, is going to be equals to the 7x squared plus 5, and we're placing that inside what? Well, my outer function here is going to be the cubic function. And again, I always recommend you guys to check it. If this is true, then f of g of x will be equals to f of 7x squared plus 5, which means that we're placing the 7x squared plus 5 inside the outer function, and the outer function was telling you to take your input, whatever it may be, and cube it, but in this case, the input is the 7x squared plus 5, and lo and behold, we do get our g of x function in return. Perfect. Now, let's practice with another one here. Alright, so for the next one here, we have h of x is equals to e to the x squared plus 3 of x. Now we have an exponential function. So what seems to be the inside, what seems to be the outside function? Rule of thumb or piece of advice, whenever you're dealing with exponentials, the exponential is the outer function. So in this case, the inner function is the x squared plus 3x. So then the outer function is going to be simply the e to the x. Now I'm not going to go ahead and check this one, but I do encourage you guys to check it to create the function composition f of g of x to see if you get h of x in return. Okay, now for the next one, I want you to try it on your own. For the next one, given the function h of x is sine of 2 of x, what seems to be the inner function and what seems to be the outer function? So try it here, and I look forward to your answers on Canvas. Alright, now I want to try one more. So what about the h of x equals to the sine of x squared? Well, notice here how I pronounce it the sine of x squared, but I could have also pronounced this one here as sine squared of x. Now, I want to emphasize this one here because it can sometimes be easy to miss. If we have sine squared of x, what this means is that we're actually dealing with the sine of x squared. Okay, now if we reinterpret sine squared of x as the sine of x squared, it's the same thing, we get to see that our inner function is the sine of x. So, if g of x is sine of x, then the outer function f of x would be x squared. And there we go. We identified the outer functions and the inner functions for, well, this set of functions here. Perfect. Now, before I talk about the chain rule, I want to give you the following scenario. What if we were given the function capital F of x is equals to 1 plus x squared, and the whole thing is being squared? What would be the derivative for capital F of x? So I'm going to go ahead and begin by taking a guess that, okay, we can probably use the power rule, because after all, I have the 1 plus x squared being raised to the second power. So I'll put here guess using the power rule. Alright, so my derivative will be here capital F prime of x is going to be equals to, alright, so the power rule tells us to bring down the power. So we're going to get here 2 times a 1 plus x squared raised to the first power. Okay, now let's see how our guess compares if we instead use algebra first. Well, if I use algebra first here, then I'm going to go ahead and rewrite our function capital F of x is going to be equals to 1 plus x squared times 1 plus x squared. Now if we go ahead and follow this, we're going to get, let's see, 1 times 1 and 1 times x squared, then x squared times 1 and x squared times x squared, which will give us here 1 plus 2x squared plus an x to the fourth here. Okay, now taking the derivative of this function, we're going to get f prime of x is equals to, the derivative of 1 is 0, the derivative of 2x squared is going to be a 4x, plus the derivative of x to the fourth is going to give us here a 4x cubed. Perfect. Now at first glance, it looks like our derivative that we obtained using algebra first doesn't quite match the derivative that we got with our guess. But I'm going to go ahead and see if I can maybe manipulate our answers here to see if I can make them match. Well, let's see. So for our derivative of the polynomial, the 4x plus 4x cubed, taking a look at this one here, and I can see that I can factor out a 4x. So I'm going to be left with a 1 plus x squared. Okay, now I do see the 1 plus x squared at least. What else can I do here? Well, I notice that this 4 can be rewritten as 2 times 2. Okay, well then this is going to be equals to a 2 times, and I'm going to put this one here in a different color, 2 times x times a 1 plus x squared. Oh, look at that. Well, now my answers are almost matching. I have a 2 times 1 plus x squared, so I see a 2 times 1 plus x squared, but I'm still missing a 2x from the guess. So it looks like our guess wasn't quite correct, but it was close. Now, how can we actually find this derivative? Well, notice here that if I take a look at the inside function, the 1 plus x squared, what is the derivative of the inside function? What is the derivative of 1 plus x squared? Well, the derivative of 1 plus x squared is the 2x that we were missing. Oh, okay. So we're not that far off. Well, let's take a look here at the chain rule that will tell us how to handle derivatives for the function compositions. And here's the chain rule in all of its glory. If g is differentiable at x and f is differentiable at g of x, then the function composition f of g of x is also differentiable at x, and its derivative is given by the following product. It's going to be f prime at g of x times g prime of x. So in other words, it is the derivative of the outer evaluated at the inner times the derivative of the inner function. Alright, so this is the chain rule. Now, if we go ahead and use Leibniz notation, it's going to be a similar formula, but it might look a little bit different. This time around, we don't call the inner function g of x. Instead, we call it u, but u is defined here as g of x. And if the outer function, we're going to be labeling it as y, which is going to be f of u. So in other words, it's simply the function composition. So if you have y and u, then the chain rule is the same thing as dy dx, so the derivative of y with respect to x is going to be equals to the derivative of y with respect to u times the derivative of u with respect to x. Now it might look different, but we're still doing the same thing. It is going to be the derivative of the outer value at the inner times the derivative of the inner function. It's all the same thing. Now, I'm going to work on a couple of examples using both types of notation to see which one you prefer. However, further down the line, when we start using the chain rule more often, because the chain rule is one of the most commonly used rules, I will be using u's instead of g. But we'll cross that bridge when we get there. Now, I just want you to be careful here though, because when we're using Leibniz notation, that the u here has not been defined, and du dx is not actually a quotient. It is the derivative of u with respect to x. So just gotta be careful there. Alright, so let's practice with a couple of problems involving the chain rule here. Okay, so let's go ahead and revisit the problems that we saw at the beginning of the lecture. So we have the functions here, we know they are function compositions, and better yet, we already identified the inner and the outer function. So now we want to find the derivatives, we gotta use the chain rule. And as usual, I'm gonna go ahead and write down the formula for the chain rule here. Okay, so here we have the chain rule, which is telling us that if you're finding the derivative of a function composition, it is the derivative of the outer evaluated at the inner times the derivative of the inner. So let's go ahead and identify the pieces here. Now luckily we already did it in the first page. So let's see, the inner function, the g of x, was equals to x squared plus 1, and the outer function was the square root function. Now let's go ahead and find the respective derivatives. So g prime of x is going to be equals to a 2x, and f prime is going to be equals to a 1/2 times x to the negative 1/2 power. Use the power rule here. Okay, now we have the functions, their derivatives. Now it's just a matter of plugging them into the chain rule. So I'm going to go ahead and plug them into the chain rule, and my answer is going to be h prime of x is going to be equals to the derivative of the outer, so it's going to be 1/2 times x. Well, now, don't forget though, it's the derivative of the outer evaluated at the inner, so evaluated here at g of x. So rather than plugging in an x, we're plugging in the g of x, which is an x squared plus 1 raised to the negative 1/2 power times the derivative of the inside, which is the derivative of g, which is a 2x. Now we can go ahead and simplify this one here a little bit more. So my final answer should look like h prime of x is equals to, now I have a 1/2 multiplying a 2, so that can cancel. Now I have a negative exponent, simply going to go ahead and bring it down. So we're going to have x squared plus 1 raised to the 1/2 power, in other words, the square root, times an x on the top here. And that's it. Here we have our derivative for h. Excellent. Okay, now I'm going to go ahead and try the next problem here. But the next problem, I'm going to be using Leibniz notation as well. So let's take a look. For the second problem, we have h of x is equals to 7x squared plus 5, and the whole thing is being raised to the third power. All right, so we already have the chain rule here. So now we just need to identify what's the inner and what's the outer function, which we already done. The inner function, g of x, was the 7x squared plus 5, and the outer function was the x cubed. All right, now for the respective derivatives, what is the derivative of g? Well, we should be getting a 14x, and the derivative for f should be a 3x squared. Okay, now, putting everything together here, in fact, let me make this a little bit smaller. There we go. Putting everything together into our chain rule, h prime of x is going to be equals to the derivative of the outer. So we're going to have a 3 times, now it's going to be the derivative of the outer value at the inside. So it's going to be 3 times a 7x squared plus 5 raised to the second power times the derivative of the inside, which in this case is simply a 14x. Okay, now simplifying things fully here, we're going to get 3 times 14, I believe that should be a 42, x times the 7x squared plus 5 to the second power. Again, I'm just going to go ahead and make this one here a little bit smaller. Just make this one here. Okay, perfect. Now, what if we went ahead and use Leibniz notation? Is it going to be any different? No, it's the same process. You're just changing the variables. So using Leibniz notation, our y is the function 7x squared plus 5 raised to the third. Now our inner function, rather than using g's, we're going to be using u's. So for the inner function, we're going to have here a u is equals to 7x squared plus 5. Now what about the outer function? Now the trick here is to go ahead and rewrite your function in terms of u. So y is a function of u. Now since we've already defined the u to be the 7x squared plus 5, then we're going to be substituting the u here. So y is actually simply u to the third power now. That's a different interpretation that we're giving it. It's all the same thing. All right, now we are going to need the derivatives, as we saw in the previous examples here. Now, the du dx, I'm going to go ahead and get it here. Du dx is going to be equals to the 14x. But now we've got to find the derivative of y with respect to u. So what would be the derivative of y with respect to u? Because now it's a function of u, and that's just going to be 3u squared. Okay, now we have all the pieces here. Let's put them all into the formula. Now with Leibniz notation here, the chain rule for a function y in terms of u is going to be dy dx equals to dy du times du dx. Okay, well, let's see. We're going to get dy dx is equals to the derivative of y with respect to u, which was a 3u squared times du dx, which was a 14x. So you see here, okay, it's pretty much the same thing. The last and final thing to do, though, is go ahead and back substitute the value for u that you got here, or the way that you define u. All right, so for our problem, u was 7x squared plus 5. So our final answer then is going to be 3 times 7x squared plus 5 squared times 14x. Now this one here I didn't simplify, but you see that it is exactly what we got here. Okay, so this is the comparison between the two approaches. If you prefer the f prime times g of x times g prime of x form, that's fine. If you want to use Leibniz notation, that's also fine. But again, like I said here, down the line, once we start taking more and more derivatives, I'm going to go ahead and reference u's quite a bit. But just know that the u is the same thing as the inner function, g. Okay, so let's go ahead and take a look at one more problem, and then we'll stop the video here. Alright, so this new function here is the h of x equals to e to the x squared plus 3x. Alright, perfect. So let's go ahead and use our chain rule here. So we said that for exponentials, it is the exponents that are the inner function. So for this one here, g of x is going to be equals to the x squared plus 3x. Perfect. Okay, now what about the other function? Well, the other function is just going to be the natural exponential function. Now, to find the respective derivatives, f prime of x, well, the derivative of e to the x is just e to the x. Now, the derivative for g is going to be equals to a nice 2x plus 3. All right, perfect. So putting everything together, the derivative for h is going to be equals to the derivative of the outside evaluated at the inside, which is an x squared plus 3x, oh, the same thing, times the derivative of the inside, which in this case was the 2x plus 3. There we go. Now, I want you guys to be very careful with this one. As it stands right now, this answer is incorrect. Now, why is it incorrect? So I want you guys to think this briefly here. So let's go ahead and pause the video and ask yourself, why is this answer here not full credit? What's wrong with it? Maybe you already spotted it. Alright, so let's pause the video and think about this. Did you spot the error? We need parentheses. Because right now, remember, we're saying that we have to multiply times the derivative of the inside. If we do not include parentheses, then you would have only been multiplying the e raised to the x squared plus 3x times the 2x. But the 2x was not the derivative for g. The derivative for g was 2x plus 3, so we gotta make sure that we multiply everything. Okay, perfect. So I think this is a good place to stop our first part of the recording. We'll continue on part 2, dealing with more examples involving the chain rule. See you there.